So we continue with Kummer theory. Let us now apply the notions introduced so far to the complex of Kummer theory. For this, we impose on the G module A the following axiomatic condition. Axiom. So this is an axiom condition for A. G module A to require H minus 1 that cohomology AI equals 1. By definition, this means we require this. Okay. The theory we are about to develop makes reference to surjective geomorphism. With finite cyclic kernel mu p. The order is called the exponent of the operator. The case of prime interest to us is when P is the nth power map mu p equals mu n, all the elements of A that is nth roots of unity. We now fix the field K. Such that mu p is containing AK is the fixing point of G. We choose a K that the fixing point of AK contains all the roots of unity and the roots of unity for every subset B of A. The KB denote mu p mu 1. Okay. KB denote the fixed field of the closed subgroup. The definition of this closed subfield is clear. So for P subset, here it says subset, we collect all those elements of GK. So this is a subgroup of GK, such that it fixes all the elements of B. And we denoted KB. If B is GK invariant, KB will be Galois. If P is GK invariant, then all the elements fixes B, then H is GK itself, n'est-ce pas? So Galois, this is a trivial field extension in this case. Why not? A Kummer extension with respect to some morphism is by definition an extension of the form. Here it's not B. Instead of B, we put an inverse image of P, of delta under P. Well, delta is a subset of A. A Kummer extension is always Galois. It is Galois group with a abelian of exponent n. We just define what is exponent. Exponent is the cardinality of the kernel. Indeed is to explain Galois of exponent n. For extension, we have the injective homomorphism. So we're looking at the Galois group of this field extension. We have to remember the meaning of this notation. The subgroup, it is a fixing field of the subgroup such that for all the elements of rho minus A, the elements of this subgroup have to fix the mu p. We call that mu p. Mu p is a subgroup, subset of A. So it should be a submodule. We constructed a map from the Galois group to the module. Yes, this is, you see, this is element of the group, but you're acting an element of the module. So of course it's still an element of the module. Mu p is in n key is because that we fix it in that way. This definition does not depend on the choice of alpha. Thus, for Kummer extension, Composite map is injectable homomorphism. Look at this. By definition, this is all the elements of GK. This is a fixing field, sorry. Other elements such that it fixes all the elements inverse image of delta, which means it is the intersection of which fixes denote this by it is the intersection of each arc, and so the fixing field of intersection is fixing by a smaller one. It's the union of the fixing. And this is by definition this. Here is written as product. Why we write product here? Because we have to remember what is the meaning of this notation. Let's come back there. And the group is intersection, and this fixing field is composite. And here, how is our group? So we wrote something not true. It's because let's recall the fixed field of the subgroup. It's not the fixed module, sorry. So here it's not fixed module. fixing field of H, which if you want, you should write in this way if you want. If you want, you should write the fixing field. As we saw, for fixing field, the Galois group is becoming smaller, it's become bigger, and bigger is in the notation is composite. Okay, so we have the composite map. It's because now it's by definition this is product Galois group of the composite field mapped to the composite of the Galois group. This is injective Y. Okay, actually this is what I already discussed. This is intersection. So it injects into the product. What is this? This is the product. Maybe, but it corresponds to this injection. It's just cardinality, also index. Okay. The following proposition says that the converse and the abelian extension of a given exponent n is a Kummer extension. Conversely, any abelian extension of a given exponent n is a Kummer extension. And what we showed just now is a Kummer extension of exponential n is an abelian extension, because we embed it into abelian. It's cyclic. This is in my sense what was confusing me. Constructs something step by step, but finally you say this is a structural thing. This is oh yes, this in this case a group homomorphism. Yes, because each step is group homomorphism. So good, no problem. Yes. And the abelian extension of exponential n is the Kummer extension. Let's recall again what is the exponent. Exponent of the operator. Exponent of the operator. Any abelian extension of exponent n is a Kummer extension. So what is a operator related to Kummer extension? Yeah, related to abstract p-adic extension. L over K. Let's go through this proof, because for me this definition of the p-adic extension of exponential n is not very clear. I suspect it just means that this group has cardinality n. I suspect. Let's say go through the proof and we'll see. It's claimed that in this case we can write precisely what is L. There is only one possibility. There is only one possibility. This notation is also not very clear. We know AL is the fixing point of GL, of A by GL. AK is the fixing point of A by GK. But you write P, because P, what is P is action from A to A. So of course it can X here. Does it mean the fixing point? At this moment is not very clear. Let's say. And in particular, if this is cyclic, then claim that L is more precisely extension of one element. We have the inverse image of delta. It's containing AL. Because let's recall that this is a definition. Because if X is in A and maybe it's not so complicated, because alpha delta is defined to be the intersection of ALP with AK. So this is obviously true. And so, for an element of A, we acted by row map it No, sorry, this is not obvious, but delta is in here. It doesn't tell you that. P inverse delta is inside the L. In other words, if you have a map, of course it doesn't tell you that. Right? Because F may not be injective. You can have 2 points mapped to one single point. This is A, I call this point B. Then F is this map. The FA is inside B, but doesn't mean the inverse of B is inside A. So you have to show it. But you say that if two elements, when they're action by P, right? And Px equals P alpha. With X in A, alpha in AL, because there is one from AL that is mapped to delta. So there are two elements, at least one element of AL who has image the same as an arbitrary element of A that is under the image of P. If this is a truth, we see that it must differ by the kernel of P, which is containing AK. This is by assumption. And therefore we conclude that the reason we write X in A to say the component is because P itself is defined from A to A. So any element here must lies in A, of course. And this is because AK itself is containing AL. L is bigger field and so is Galois group. It's smaller. And so the fixing point is bigger. Therefore we have this. On the other hand, the extension over K is the composite of cyclic subextensions. For it is the composite of its finite subextensions. Why is it true? Because this is abelian extension. And the abelian group is a composite of cyclic any abelian group is the direct sum of cyclic groups by the structure theorem. but this is not very clear for me. It is a composite with finite subextensions, and the Galois group of a finite subextension is a product of cyclic group, which may be interpreted as Galois groups of cyclic subextension. So here is the claim. We claim it is the composite of its cyclic subextension. What we know is it is a composite of its finite subextension. We don't know it's cyclic or not. Yes, so there is a proof. So it's a 4. It is the composite of its finite subextension, and the Galois group of finite subextension is a product of cyclic groups. Yes, because finite abelian group is product of cyclic group, which may be interpreted as Galois group of cyclic subextensions, because the Galois group of cyclic subextensions are cyclic group, and cyclic group can be interpreted and the Galois group of cyclic subextension. The logic here is if you can show all the cyclic subextensions is contained here, and conversely this itself is containing L, and L is composite of cyclic subextension, and we prove that L equals this Kummer extension. Okay, we'll now go through the proof. Let's see the result. As the main result of general Kummer theory, we now obtain the following. The correspondence is 1-1 correspondence between the groups delta such that abelian extensions of exponential n. Our question about exponential n for the exponent n, we think it's the dimension of the abelian extension. Actually, there is nothing to do with n for the result stated. It's just say if the abelian extension of some finite exponent. Well, here we say if m over k is of dimension d, then we denote this by d prime, I think. That's why here divided by n. We can say, we can guess the exponent is the dimension of the Galois group. The dimension of the field extension is the cardinality of the Galois group. So there is bijection between the groups delta and the abelian extensions. Knowing abelian extension L, you get the delta by take the fixing point of P of AL. So you first calculate AL. First calculate AL. And then you take the fixing point, the intersector is AK. And we have canonical isomorphism. The converse direction is, as I said, finding delta, you construct L in this bijection. So you give out that extension of exponent n in this case. Remarks and example. If L over K is infinite, this group has to be interpreted as a group of continuous homomorphisms. As the chapter group of the topological group. The composite of two abelian extensions of K of exponent n is again the same type, and all of them lie in the maximum abelian extension of exponent, and is given by and for the Pontryagin dual. We have isomorphism by 3.3. In that case, we took delta to be the whole of AK in that remark. In this case, it's this homomorphism is L. This, but if you take delta to be AK, then we denote this. We call this what? What do we call this? We call this maximal. The maximal abelian extension exponent. Right? So maybe the exponent n here is really only depends on rho. Maybe it's just cardinality to the kernel of the cardinality of the kernel of rho is n. So it's just, so you see, when you change the field, it doesn't change the extension of n, so it's n, so this should be related to this rho, I think. Yes. So it should nothing to do with the dimension, maybe. Just the cardinality of p, maybe. And we don't have this result. We have the abelian group of the maximum abelian extension. So it's going this way. If K is actually a field positive characteristic, then K bar is separable color of K, and then A can be chosen to be an additive group. Okay, so you just regard it as an additive group. And P to be the operator. Okay, extra 3.1 is indeed satisfied. We have completely generality proposition over cyclic finite field extension. We already have this. The extension arc is the main normal basis. This means that L is a geometric induced module. Hence we have the trivial cohomology group. Yes. And to prove this, you always use the normal basis theorem. Because this is a cyclic finite. So I guess this is true for any abelian, right? Abelian. And then you have the normal basis. Something L. The Kummer theory with respect to the operator is usually called Attinschneier theory. The Shave application of the theory developed above is to a case where J is absolute Galois group, an actual field, A the multiplicative group of algebraic closure, and P the nth root map of some natural number n which is relative prime to the characteristic of K. In particular, is arbitrary if characteristic is 0. X realm is always satisfied in this case, and it's called Hilbert 90 because this statement occurs and sets number 90 among the 969 theorems in Hilbert's famous notes article. And there we have the statement for cyclic field extension, and I always have this. In other words, any element of the multiplicative group of L it is the image of norm. Of norm 1 is of this form. The image of sigma, so it's sigma count beta and beta inverse. R from norm 1. Here this sigma, this beta, sorry, such that we have this. If now the field K contains the group mu n, as root of the unity is the operator, the operator has exponential n. And we obtain the following corollary, which is the most important special case of theorem 3.3, that's the normal correspondence. Let n be a natural number which is relative prime to characteristic of the field K and assume them using K. The Abelian extension with exponential n corresponds 1, 1 to the subgroups okay, because as we mentioned, usually it's for AK. In this case, we have a specific AK. We take A to be multiplicative group of the separable closure. And then we have special AK, which is the fixing point. Come here, star. And so the theorem tells you that those containing AKP and containing AK is it? Is it so? Tout à fait. Exactly so. We have the correspondence. And the Galois group is given in this way. So this is a number field. Sorry, what did I say? This is for a real field, it's also abstract. This is not necessarily a number field, sorry. It's just arbitrary field which contains the multiplicative group through the unity group. Sorry, have the one correspondence to describe all the Abelian extension of exponent. For me, there's still problem. So it's not very clear what are field extension exponent and step. This problem lying here. You have to fix module A. What is module A? You have to first fix the field. You have to, right? You have to first fix the field. Actually, if you look at Wikipedia, you will say that the definition of exponent of a group. Let's look at Kummer extension. A Kummer extension is a field extension over K which where for some given integer n, we have the first condition is that it contains the nth root of unity. As far as is mu keys contained in K, okay? The second is our K is a Abelian group of exponent n. So what is exponent? What is exponent? Actually, you will say it is the order of all the elements of this group, and you look at the greatest common divisor. It is the greatest common divisor of the order of all the group. The exponent of a period group which is the sorry, not the greatest common divisor, it's the least common multiple. Sorry, if it exists of the order of all the elements of G. It is a divisor of cardinality of G, of course. Although we didn't notice we reuse this condition, but for example, when n equals 2, the first condition is always true if k has characteristic not equal to. I mean, it has plus minus 1. The Kummer extension in that case includes quadratic extension. You have to include all the roots of the unity. Whereas in K is a non-square element. This is an example of Kummer extensions, okay? By the Euro solution quadratic equations and extension of degree 2 of K had this form. The Kummer extensions in this case also include biquadratic extensions and more generally multi-quadratic extensions. Okay, as chapters 2, there are no such Kummer extensions. Some examples just. So that's what we were talking about. Hilbert's 90, which is the main basis of this corollary. It makes the following generalization to arbitrary Galois extension. Okay, go back to M and not. Let J be a finite group and A a multiplicative G module. A one cocycle or crossed homomorphism of G with values in A is a function satisfying definition of one cocycle. This corresponds to semi-linear homomorphism. Semi-linear homomorphism, yes. That's the action of tau on F sigma and then F factor on tau. The one cocycles form a abelian group for every small a in A. The function is one cocycle. For one hand, this functions FA are called one coboundaries and form a subgroup. Now we've defined the Euroleague group homology. And the generalization Hilbert's 90 gives for any finite Galois. Didn't see cyclic this time, it's just Galois, finite Galois, field extension. I had that each one is trivial. Actually, here is the L star, and you can put also, if I'm correct, GLN L, I think, yes. So this is a subgeneralization. This proposition will only be applied once in this group.